students, this is Shefali Ghutke, currently working as Assistant Professor in Civil Engineering Department at Tulsiramji Gaikwad-Patil College of Engineering and Technology. I welcome you all for today's Fluid Mechanics 1 lecture. In today's lecture, we will going to see fluid and its properties. Basically, fluid mechanics is categorized into three parts: fluid statics, fluid kinematics and fluid dynamics. In fluid statics, we will going to study of the fluid when it is in rest condition or in static condition. In fluid kinematics, we will going to study the motion of a fluid without considering its cause of a motion. And in fluid dynamics, we will going to study about the motion of a fluid with considering the basic cause of a motion. It means in fluid dynamics, we will consider force which is acting on the fluid, which is based on Newton's second law of motion. In that, fluid is assumed to be ideal. So first question which arises is what is fluid? Okay. So fluid are the substance that deform continuously under the application of tangential force, no matter how small it may be. Fluid is a substance that is capable of flowing. Okay. If suppose we are applying the force and the force is very small, even in that case, fluid is capable of flowing. Fluid has no definite shape. It assumes the shape of its container. When you put water into a glass, it takes a shape of a glass. Okay. Basically, both liquid and gases are fluid. There are three types of matters, right? Solid, liquid and gases. Both liquid and gases are considered as fluid. So these are the some example of fluids: water, milk, kerosene, petrol and emulsion. So first we will going to study about very important fluid properties. Properties of a fluid determine how fluids can be used in engineering and technology. They also determine the behavior of a fluids in fluid mechanics. These are the important properties: density, viscosity, surface tension, capillary action, specific weight and specific gravity. One by one we will discuss all these properties. First, we will see density. Density is the basic property of fluid. It is defined as the mass of a fluid substance per unit volume. It is the ratio of mass to the volume. In other words, we can say that it is the ratio between mass and the volume of a fluid. Mass is represented by M and volume is represented by V. So the density is denoted by the symbol rho. Okay. And its unit is kilogram per meter cube. This is MKS and CGS. Unit will be gram per centimeter cube. 1 gram per centimeter cube is equal to 1000 kilograms per meter cube. So we can say that the density of a water is 1000 kilogram per meter cube. Okay. Next property of fluid is viscosity. When two adjacent layers of a fluid are in relative motion, then they resist the motion of each other. Such a fundamental property of a fluid is known as viscosity. Suppose there are two layers, okay, there are two layers which are moving. Okay, so they basically resist each other motion. So this phenomena is known as viscosity. Viscosity is the fluid property that determines the amount of a resistance of a fluid to the shear stress. It is the property of a fluid due to which fluid offer resistance to the flow of one layer of a fluid over the another adjacent layer. Next is Newton's law of viscosity. According to Newton's, the shear stress which is acting on the layer of a fluid at a particular distance y, we are considering at a particular distance of a y. Okay, shear stress is acting. So basically this shear stress is directly proportional to the rate of angular deformation. So the Newton's law of viscosity formula will be shear stress is equal to mu into du by dy. This du by dy is nothing but velocity gradient. This velocity gradient is maximum at the wall and decreases in transverse direction of the flow. So we can say that shear stress is maximum at the wall. Suppose the fluid is flowing. Okay, in that condition we can say that the shear stress is maximum at the wall and shear stress is zero at the center. It means at the axis the shear stress is zero and at the wall the shear stress is maximum. This mu is nothing but coefficient of viscosity or dynamic, or we can say that absolute viscosity. Viscosity basically it is an important property of a fluid. Okay, viscosity means viscous nature of a fluid. There are two types of viscosity, dynamic viscosity and kinematic viscosity. So the dynamic or shear viscosity of a fluid expresses its resistance to the shearing flow, where adjacent layers moves parallel to each other with different speed. Suppose there are two layers which are moving with different speed. In that case, these two layers will resist each other motion. It means they are offering resistance to the shearing flow. Okay. So basically this is called as dynamic viscosity. Dynamic viscosity is nothing but the Newton's law of viscosity, which is expressed using same equation, tau is equal to mu into du by dy. Next important property is kinematic viscosity. Kinematic viscosity, also called as momentum diffusivity. It is the ratio of dynamic viscosity mu to the density of a fluid rho. So this is the symbol of kinematic viscosity, which is equal to dynamic viscosity divided by rho. This kinematic viscosity is equal to meter square per second. Its unit is meter square per second in MKS, and in CGS we can say that one stroke is equal to 10 raised to the power minus 4 meter square per second. This mu is nothing but dynamic viscosity. Its unit is Newton second per meter square or Pascal second. Okay, and this is the density rho, density of a fluid, which is in kg per meter cube. So the next property is surface tension. A molecule in the interior of a liquid is under attractive forces in all the directions. Here in this picture, we are considering two molecules. This is molecule A and this one is molecule B. Okay. Suppose this molecule A is inside the liquid and this molecule B is at the surface of a liquid. Okay. So this molecule will be balanced molecule and this molecule will be unbalanced molecule because this one is at the surface. Okay, as you can see in this picture, the resultant force which is acting in this molecule A equal to 0. So this one will be balanced. However, a molecule at the surface of a liquid, this one B, is acted on by net inward cohesive forces, that is perpendicular to the surface. Cohesive force means सेम नेचर के मॉलिक्यूल जब अट्रैक्ट होते हैं, ओके, हैंस इट रिक्वायर्स वर्क to move the molecule to the surface against this opposing force, and the surface molecule have more energy than the interior ones. Higher the force of attraction at the surface of a liquid creates stretched membrane effect. When you put water into a glass, in that case you will see there is a one layer, okay, one layer at the surface of a liquid. This layer is nothing but, this layer is because of the surface tension. I will give you one example. Have you seen that some insect, some small insect travel at the surface of a liquid? This is because of the surface tension. Because at the surface of a liquid there is a membrane. Because of this membrane, this small insect can travel. Okay. So this surface tension is represented by sigma S, the surface force resulting from molecular attraction at the liquid surface. So the unit of surface tension is Newton per meters. Force is equal to surface tension into L. So the formula of surface tension will be equal to force divided by length. This Fs is nothing but surface tension force, which is in Newton. This is surface tension, which is Newton per meter, and this L is nothing but length over which the surface tension is acting, which is in meters. This F, this surface tension force, we can say that sometimes tensile force, that is the effect of a cohesive force at the surface of a liquid. Next is capillary action. Capillary action is the property of a fluid to flow in a narrow space without the assistance of and in opposition to the external forces like gravity. When a tube of a very small diameter is immersed in a liquid, then the liquid may rise or it may be fall inside the tube. This rise or fall of a liquid depends upon the wetting and non-wetting nature of a liquid with the glass tube. So this whole phenomena is known as capillary effect or capillarity. This effect can be seen in the drawing up of liquids between the hairs of a paintbrush in a thin tube in a porous material such as paper and plaster, in some non-porous material such as sand or in cell. It occurs because of the intermolecular forces between the liquid and surrounding solid surfaces. This is the example of capillary action. As you can see in this picture, the tissue paper is able to absorb the ink because of the capillary action. Basically, this capillary action is based on wetting and non-wetting phenomena of a liquid with the available surface. This wetting and non-wetting is basically because of the adhesive and cohesive nature. This is the example when glass tube is placed inside the water, and here the glass tube is placed inside the mercury. Okay, as you can see in this picture, when you put a glass tube inside the water, in that case the level of the water is raised. This one is narrow tube, okay, and this height h is represent rise of a water into this narrow tube. Okay, so we can say that when we put a glass tube into the water, in that case the level of a water will rise in the glass tube. When we are talking about mercury, when we placed mercury in a glass and when we placed a small tube inside the mercury, in that case you can see in this picture the level of a mercury is not rising, it is falling down. This is because of the wetting and non-wetting phenomena of a liquid with glass surface. Next is type of fluid. Fluid can be classified into 5 basic types. They are ideal fluid, real fluid, pseudoplastic fluid, Newtonian fluid and non-Newtonian fluid. So the first one is Newtonian fluid. This is basically rheology. Okay, rheology means it is a branch of a science which deals with the study of a different type of a fluid in a flow. So this is rheology. Okay. First is Newtonian fluid. Fluids which obeys the Newton law of viscosity are called as Newtonian fluid. For a Newtonian fluid, viscosity is entirely dependent upon the temperature and the pressure of a liquid. Example, water, kerosene, petrol, air, mercury. These are the different type of emulsions. Okay. Next type of fluid is non-Newtonian fluid. Simple, non-Newtonian means fluid that do not obey Newton's law of viscosity. Example, bluffer, oblate, suspension of a starch in a water, paste, gels and polymer solution. Basically, there are 2 types of fluid in this category in non-Newtonian fluid. First one is time-independent fluid and the second one is time-dependent fluid. Time-dependent fluid means thixotropic and rheopatic fluids. And time-independent fluid means pseudoplastic, dilatant and Bingham plastic fluid that we will discuss further. This one is pseudoplastic fluid. This pseudoplastic fluid is time-independent fluid. A fluid whose apparent viscosity or consistency is decreases with increases in shear rate. As shear rate increases, in that condition, the viscosity of a fluid will get decreased. This type of fluid is nothing but pseudoplastic fluid. Example, blood, milk, quicksand, ketchup. Next type is ideal fluid. Ideal fluid is a fluid that has no viscosity. Basically, they do not exist in nature. Practically, there is no ideal fluid. This type of fluid is incompressible in nature. So this is flow of an ideal fluid and this one is flow of a viscous fluid. As you can see in this picture, this is the example of ideal fluid when the fluid particles moves in a straight direction. Okay, this is ideal and this one is viscous fluid. Okay, this ideal fluid has no viscosity and is incompressible in nature, and real fluid will be compressible in nature. Next type is real fluid. Real fluids are compressible in nature. This type of fluid having some viscosity. The real fluids implies friction effects and they exist in nature. Example, kerosene, petrol, castor oil, likewise. This is the velocity distribution of a pipe flow. This is the pipe in which the water is flowing. This is the velocity distribution of ideal fluid and this is the velocity distribution of real fluid. It means the velocity is varying. As you can see in this picture, in ideal fluid, velocity is constant, but in actual, the velocity will not be constant at boundary, or we can say at the wall. The velocity will be 0, and at the center, velocity will be maximum. So this is how velocity distribution profile will looks like. So this is the rheology diagram. This represents Bingham plastic. Bingham plastic also called as ideal plastic. Example is toothpaste. And this one is Newtonian fluid. A fluid that obeys Newton's law of viscosity. Newton's law of viscosity is tau is equal to mu into du by dy. Mu is nothing but dynamic viscosity and du by dy is nothing but velocity gradient. Okay. And this line represents shear thinning. Okay, this shear thinning type is pseudoplastic fluid. This one, pseudoplastic fluid, in which the viscosity, apparent viscosity of a fluid decreases as the shear stress increases. And this one is shear thickening. Okay, shear thickening is dilatant. Dilatant types of a fluid are called as shear thickening fluid. Okay, example will be solution of sugar. When you put sugar into the water, in that case you can see the solution will get thick. So this is the example of shear thickening. We can say that dilatant and rice starch solution. Okay, in shear thickening, the viscosity of a fluid will get increase as the shear stress will decrease. Thank you for listening.